Okay, so we're going to pick up where we left off on Friday with this idea of how equal periodic payments can be used to not only build towards an investment, but also to pay off a loan. I'm going to encourage you on your own to pause the video, take a minute right here and read through how a loan is initially structured, how monthly payments are calculated. And then once you are done reading, unpause the video and go ahead and turn to the next slide. So we left things on Friday with this idea that when you go to a financial institution or anyone who's going to give you money to get an item now, whether it's a house or a boat or a couch or anything you're taking a loan out for, maybe it's to start a business. The idea is that the person or entity that is giving you the money is giving you a present value, a value of money now. But they're going to want to make sure that they consider what the future value would be of the present value of your money if they had kept the money, left it in, and allowed it to gain interest. And then what they're going to do is calculate what your monthly payment would be if it was an equal and periodic payment. So for a minute, I just want you to remind yourself of where we left things on Friday, with this idea being that it's our job to use equal periodic payments, the value of an annuity, or the idea and formula of an annuity to build towards basically what would be the bank's investment had they not given you the cash. And then we got to think in terms of what we need information on. These both here are referencing the future value of money, and yet often what we really need is to be able to discuss the present value of whatever it is that we want to purchase. Our home, our house, our car, our business. We want to reference, hey, how much is the institution giving me today? So often we need another formula. So the formula that we're about to create and then use is considered our present value formula to reference how we work with loans. Future value goes towards investments, present value goes towards loans. You're going to hear me say that a lot over the next few days. So what we're going to do is, since both of these are equal to future value, we can set them equal to each other. And then watch and pay close attention here. We're going to stop worrying about the future value label so that we can solve for the present value. Now, the initial step of solving is pretty quick and easy. It's just a nice, simple division that allows me to get the present value by itself. But as you can see on this right-hand side, the formula is a little messy. So what we're about to do in the next 4 to 5 lines is clean up this formula. We're going to do that by first rewriting the denominator. So I'm going to drop what's in green down here in red. And then instead of dividing by 1 plus I to the n, I'm going to multiply by the reciprocal. And then I'm going to remind myself how fractions work. I can think of this as r over 1. I can multiply across the top to give me r times 1 plus I to the n minus 1, technically times 1, though obviously I wouldn't need that, all over I times 1 plus I to the n. And then, as a reminder, I refer to this often as the butterfly effect. I can allow my denominator to split up the numerator. So the way it would look is, if I detach and keep that r detached, I could have kept it detached from the beginning, then I can say, all right, you know what? This is actually 1 plus I to the n over my denominator minus 1 over I times 1 plus I to the n. In reality, again, I reference this as the butterfly effect. It goes here and here once I detach that r. And then items start to clean up. These can cancel. And what I'm left with is r times 1 over I minus, now watch this here, this is going to be important. Notice that in order to add or subtract denominator or fractions, I need there to be a common denominator. So if you notice here in the black denominator, I almost have the I that I have down here in the green denominator. So if I divide by something that is attached to an exponent, I can kick it to the other part of the fraction with the negative exponent. And in this case, then, I have common denominators. And what I have in the final step is my formula. R times 1 minus 1 plus I to the negative n all over I. This is the present value of an annuity. Now, where does this especially come into play? Do me a favor and go ahead and hit pause again. And on your own, just see if, just by intuition alone, and the sheer fact that we have already worked with the future value of an annuity formula, see if you can hit pause, read through that to yourself, and actually set up what the formula would allow you to solve for. Meaning, use the formula to solve for the question in A. Go. Okay, so we're trying to buy a house. Your bank has offered you a loan at 4.75% interest for 30 years. And you decide in your family that you can afford a monthly mortgage payment of $900. The question is, what is the largest amount that you could afford to borrow? So as we start to do this, we can say, when I am thinking about the word borrow, that I'm referencing immediately that idea of when am I borrowing it? Today. Therefore, I'm talking about present value. So asking what is the largest amount that you could afford to borrow is saying, what's the present value of the money that I could afford to take out from a bank? If I pay $900 for my equal periodic payment times 1 minus 1 plus 0.0475 all over 12 to the, and this is where this becomes important, so it's a little hard to see this exponent here, to the negative 360th. 12 times 30. Now again, that exponent is just on this part alone. This is all over 0.0475 all over 12. So when it asks for what is the most that I can afford to borrow, I can actually just put that value in. And we're going to just put this in our calculator here. So just as a quick reminder, you're going to continue to need your good calculator. And I know I've showed you this a couple times, but I'm going to show it to you one more time just so you can get in the habit. I think it helps if you put it in one line. And the key to it is just to remember to include all the parentheses that you need. 0.0475 divided by 12, and again, it's just that piece that's being raised to the, and now this becomes important, negative 360th. Then we close that numerator, divide by the denominator, which also needs to be in parentheses, and I have that value that I could purchase a home for $172,530. What is perhaps Equally as interesting is question B. So if you would for me, go ahead and hit pause again and read through the idea in question B and see if you can then solve it. Go. Okay, so when we go to answer part B is where we really want to pay attention to the algebra of this. I want to emphasize that when we're thinking about part A and we find this $172,530.35, that is, again, a present value. So when I start to talk about what happens, how long will it take to pay this back, then I am using the present value formula. This is 1 minus 1 plus 0.0475 over 12, and here's the key again, to the negative t, all over 0.0475, sorry about that, all over 12. And we then need to go through the algebraic steps. So, first of all, I'm going to remind you, I need to get rid of these two things first. So we're going to divide by 1,000. And I want to make sure, if you haven't already, that you include this in your notes so that you have a reference point, especially with a trickier equation like this to solve. This is all over 0.0475, all over 12. The good news is, just from working with some of you last week, I am aware you're in pretty good shape when it comes to solving. I know most of you know that we have to multiply by this to get rid of it. So I'm going to multiply this side by 0.0475 all over 12 here and here. So if you're following along on your calculator, I'm going to take this amount, divide by 1,000. Then, I didn't divide by 1,000 up here. Sorry about that. That should have been 172. That should have been here. Your decimal should have been there. Sorry about that. 172. Then I'm multiplying by 0.0475. Oops. Divided by 12. I get that value, and now pay really close attention because at this point I have this 0.68. I'm going to just, for my the notes itself, I'm going to abbreviate that to 0.683. Obviously, I'm going to retain that value. So I'm going to write 0.683 here equals 1 minus this stuff. And again, we're especially just walking this through for, oops, that's a negative t. We're walking this through so that you have in your notes what this algebra looks like. I now need to subtract 1. When I subtract 1, whoops, I have that, negative 0.317. But what is key here, and a little bit trickier than the future value problem, is that there is a negative outside here. So before I ever take the logs, I need to make sure I divide both sides by a negative 1. I then have 0.317 equals 1 plus 0.0475 over 12, all to the negative t, because both this negative and that negative have canceled. And now, as you know from our conversation last week, at this point, I can take the logs. So I can say that this exponential equation can be rewritten like this. You also can think of it as taking the log of both sides. My base here is 1 plus 0.0475 all over 12 of 0.317. This is going to give me an answer that is negative t, which we're going to address here in a second. So I'm going to go up here in my calculator. Notice I'm going to have to go ahead and multiply by -1 to make sure that that's positive. I'm going to take the log of both sides with the base of my 1 plus I. And here, I'm going to have my calculator draw this. Notice, I get a negative answer. That's a good sign because my negative answer has to give me negative t. So I'm going to write that as negative 290.76. This is negative 290.76. And then it becomes important to recognize the actual question itself. The question said, if you paid $1,000 per month, how long would it take to pay it back? So this gives you 290.76 as a total number of payments. We've also referenced that as N. And the key is this, that the 290th payment won't cut it. So typically what we'll say is that it is one of two options. You could say that it's 290 regular payments of $1,000 plus interest, which eventually I'll teach you how to calculate that interest. Another way to say it would be, you know what, it's going to take 291 payments. 290 payments of $1,000 and then an additional interest. So I want to just point out a couple other things before you start to work on worksheet 6, and then we're going to be done. One of the questions that is going to be consistently asked is, how much did you pay in total? And it was loosely asked in different ways in worksheets 4 and 5, and tomorrow I'll take questions on that. But when we talk about paying in total, I just want you to draw your attention to this. When I think about my $900 at the beginning of the problem, we paid $900 360 times. And so we paid $324,000. So one question would be exactly what I just said. This here is your total payment. Another follow-up question would be, how much interest did you pay? Well, when I want to talk about interest, I want to think about how much did I pay in total minus how much my present value of my money is. So this would give you your interest amount by subtracting. So this becomes an interesting evaluation of money if you're careful here. We can take 324,000 minus 172, 530 and 35 cents to get interest of 151,469 and whatever those cents are in your calculator. Now, ideally, the one thing you should quickly note is, good heavens, that is almost double. We know from last week that we looked at other payments that were exceedingly high. The other thing I want to just point out is that in Part B, you, compared to A, paid $1,000 291 times. Now, at this exact moment, recognizing that it really is 290 in interest, but let's just say for our intents and purposes, at this exact moment with what you know, we make 291 payments. That means we would pay $291,000. So here's what's worth noting. In option A, you paid $324,000. In option B, you paid $291,000. So just as a little bit of a preview, and then we're going to wrap this up so you can work. This gives you a preview into a question that would sound like this. much was saved by changing your payment from $900 to $1,000. Well, if originally I would have paid $324,000 and now I only have to pay $291, that is good news because I just saved $33,000. Now that's over the long haul. That is over 30 years worth of time, obviously. And so we'll talk more in the next couple days about the significance of that in terms of making decisions for ourselves. Excuse me. But for now, that's the information you need to know to proceed with worksheet number 6 and how to use the present value formula when we're talking about annuities that are paying back loans.